Welcome to Your Math Explained, where we make math simple and clear. My name is Julian, and today we'll look at two problems that revolve around the idea of computational thinking. The first problem is for grade 9 and 10 students, and the second problem is for grade 11 and 12 students. In both problems, we use a systematic algorithm to identify patterns to make progress in a problem. Pause the video now if you haven't had a chance to read it, otherwise, let's jump in. One of the things that I noticed first about this problem is that I have to flip 3 coins at a time. Instead of jumping straight into a problem where I already have 16 white coins facing up, I'm going to create a situation where there's just a few facing up and a few facing down. So I'm going to have this diagram here. Hopefully that is clear, that there are 6 white sides and there are 6 blue sides. The goal here isn't to figure out how many steps it would take, because if I have 12 coins, it's pretty easy. We just need to flip the remaining ones 3 at a time and we'll get the result. What I actually want to notice is that I've got 6 whites and 6 grays. I'm more focused on what the net change could be. So, of course, I could flip 3 of the white ones to grays, and that would result in 3 white and 9 grays. This is one potential outcome from my flip. The other potential outcome that I could have is not flipping all 3 white ones. So let me show you in the diagram up top. So if I had that original state of 6 white and 6 gray, I could also just flip one of these to a blue and then flip the 2 blue ones at the bottom to make them white. That's still flipping 3 coins. And so what's the net result here? I have a situation where I can get 7 white and 5 gray. Now, if I can do this, I could also make 5 white and 7 gray. I can go the other way if I really wanted to. So what we notice is that I can either have a net change of 3, focusing on the gray side or the white side, doesn't really matter, the net change of 3, or I could have a net change of 1. And that's going to be important for me when I model it out later. So that's one fact that I would want to keep in my head for now. The second fact that I want to keep in mind is how I could end this process. If I wanted 0 white and 16 gray as the final result, I would want my previous step to be 3 white and 13 gray. So I'm kind of working backwards here to imagine what situation I would like. So that's what I would want to get to. Now, of course, it's not always going to end up being 3 white, so I want to make use of this idea of having a net change of 1 to get myself down to this 3 white situation. That's my goal. So let's try to model it with the actual question here. If we have 16 white coins, if we have 16 white coins, so 16 white and then 0 gray, I would like to flip as many white coins to gray coins as possible until I get down to somewhere close to 3 white coins. So I would do 13 white and 3 gray. That's one step. My next one would be 10 white and 6 gray, and then 7 white and 9 gray, and then 4 white, and then 12 gray. So we've gotten ourselves into the situation where I've got 4 white and 12 gray, and looking at how I can do my net change, because I know that I can do a net change of 1, my next step would be to make it 3 white and 13 gray, so that I can get that second to last step, and then finally, my last step would make it 0 white and 16 gray. So counting the number of steps that we've got here, we did 1, 2, 3, 4, 5, and then that's the sixth step, the answer for 16 coins is 6 steps. And now we have an extension problem where we actually want to start with 2026 white coins, and we would like to turn them all gray. So if I were to follow the same strategy that I've used, I want to get down to this number that's close to 3, potentially 4, so that we can complete our final steps. If I were to generalize what we've done, what we can see here is that we got ourselves down and left ourselves with 4 coins left. So how many steps does it take to get us down to 4 coins? And then I added 1 step to make it a 3, and then a 1 step to do the final flip to turn them all into grays. So with the 2026, let's see how to get down to just 4 coins left, meaning I want to flip 2022 of them so that there's 4 whites left. And conveniently for us, 2022 is actually divisible by 3. That works out to 674. So in the model, we would be doing like 2023 here, and then 3 gray, 2020, and then 6 gray. So if we move all the way down, we will get 4 white and a bunch of grays that we actually don't really care about. We just have 4 white coins left, and we've shown through the division here that that's 674 steps. Our next move is to create that net change of 1 so that we get 3 white and then a bunch of unknown grays. Again, we don't really care about that. And then we have our final flip to make it 0 white and 2026 grays. That's allowing us to get rid of all the whites. So really, our final answer for this extension would be the 674 plus the 1 step to turn it into a 3 plus another 1 step to get it all gray. That would be 676 steps altogether. In this second problem, for our grade 11 and 12 students, we're being asked to compare the list of numbers that Imani could get from 0 to 4 button presses to the numbers that could be generated from exactly 5 button presses. And we want to notice how many different numbers are not on her existing list. So in this specific problem, there are a few things that I think I want to draw your attention to. It is the button presses of R and B. So when we look at R, it's switching the thousands and tens. When we look at B, it's switching the hundreds and ones. We don't need to really care about which order those buttons are being pressed because they are not going to interact with each other. So what we want to notice is these two don't interact. And that means BR is the same as RB. So that's certainly one helpful tool for us later. When we look at the yellow, we'll notice that it does change everything because it interacts with both the R and the B unit. So we will have to be very careful around the yellow button being pressed. One additional item that's going to be very helpful is that we notice RR is a pointless move. If we switch the thousands and tens unit once and then switch it back, it'll just revert to its previous number. So it's not giving us a new situation. So RR is not something that we need to consider. We don't need that at all. Same thing with BB and same thing with YY. These are just situations that we don't really care about. They don't matter. So those are two helpful facts that we'll utilize as we start to model out the different buttons that we can press. We'll play around with the tree diagram first. So I'm going to model the different buttons that we can press with a tree diagram, but I won't actually put in the numbers. I think it's important for us to conceptually understand what buttons we should be pressing and what buttons we don't need to press. So I'm going to model that with the letters, and then after I'm done the tree diagram, I'll pause the video so that you can try to keep track of the numbers that are being changed. And then once we're done, I will unpause the video and you'll see all of the numbers within our tree diagram. So let's get started. If we started with a number of 1, 2, 3, 4, we can certainly press any of the three buttons, R, B, or Y. As mentioned earlier, when we look at the second step, so this is our first button, now we're on to our second button press, we don't need to consider R again, because RR would just revert back to its previous state. We're gonna really only need to consider B and Y. When we're in our blue button state, we have the choice of R or Y. We don't need to hit B because that would revert back. So Y is certainly one case we need to consider. I'm not even going to put R here, because what we had mentioned earlier was that BR and RB are always the same. So without making our tree diagram more complicated by adding more branches, we are always just going to go RB. We're never going to go BR, because that will take care of the unique numbers that could be generated. Finally, we've got Y, so that can produce a button press of R or B. That would be my step 2. We repeat this process. So in step 3, if we were to go with the blue there, we're going to create a yellow. From here, with the yellow press, we're going to get either B or R. From this yellow, we can get B or R. From the red, we can go to yellow or blue. For this last blue state, we don't need to go to R because that would be RB. We can't hit blue because that would just revert back. So all we get is a yellow choice here. Now that we've got our third button press, I think we're going to pause the video here and we'll check to see if anything gets duplicated and remove those branches first. And these are our numbers when we fill them in with the button presses. And what you'll realize is that there are some duplicates already. We see that 2, 1, 3, 4 happens twice, so we'll cross out one of them. And then also 1, 2, 4, 3 is one that shows up multiple times. There's one up here as well. And I think it's worth noting what's happening to create these duplicates. We see that YBY created the exact same result as BYB. And then also YRY is creating the same result as RYR. So while it looks kind of daunting here in this third button press because we had so many numbers, 2 of them don't actually count. So I'm just going to put a box around the ones that we have left over. 3, 4, 5, and 6. And we just want to branch off from those ones. So let's start button press number 4, and we'll see what buttons we can press. So from this yellow one, we're going to be able to go with R and B. From the blue, we'll go with Y. We don't need to go R because we're going to do RB down here. We said that we're always doing RB. With the blue, we can go to yellow. And with the red, we're going to go to both yellow and blue. And then finally, we can go yellow from blue. So these are the new branches that would be created from step 4. And I think we can probably just fill in the numbers right now. So this is going to be 1, 4, 2, 3, 2, 3, 1, 4. And then we've got our yellow. That's going to be 2, 3, 1, 4. And then again, we see some duplicates already. So we'll have to get some cancellations going right after. We've got our blue, that's 1, 3, 4, 2, and then 3, 2, 4, 1, and then 4, 1, 3, 2, and then 1, 4, 2, 3, 3, 1, 2, 4, and finally we have 2, 1, 4, 3. So these are the numbers for our fourth button press, and we see some duplicates. 1, 4, 2, 3 is showing up multiple times, so I'll cancel that one out. We also have 4, 1, 3, 2. So I see a 4, 1, 3, 2 right here, and 4, 1, 3, 2 has also shown up after step 2. So we're going to cancel that one out. So we've got 2 and then 3, 2, 4, 1. I think that one shows up as well. That was also from button press number 2. And finally, 2, 3, 1, 4 showed up twice in this state. So we've got those ones canceling out, which means if I put a box around the remaining numbers, these are the unique values that Imani would have on her list. So we've got all these ones here, and let's just do a quick count just to see how many there are. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Perfect. There are 20 numbers on Imani's list. Okay, our job is to figure out what numbers you can get with 5 button presses. So we just have to continue going to get our 5th branch. So our 5th button press, and we're going to just utilize that same strategy. R can go into Y and B. B can go to just Y. We don't need the R. This B, we only need to go to Y. This B, we don't need to go to R. We just need to go to Y. And then Y, we got to go to B and R. So this will create the numbers in our 5th state, which is not too bad. There's only 1, 2, 3, 4, 5, 6, 7 of them to keep track of. So going from top down, hitting the yellow button would be 3, 4, 2, 1. And then the blue there would be 1, 3, 2, 4. That's switching the hundreds and ones, yeah. And then the yellows here would be 4, 3, 1, 2, 2, 3, 4, 1, 4, 1, 2, 3. And then hundreds and ones would be 2, 3, 4, 1. And then the red would be thousands and tens, so 4, 1, 2, 3. So these are the numbers that we have from our 5th button press, and we notice that there are some duplicates already. So 4, 1, 2, 3 showing up twice. 2, 3, 4, 1 is showing up twice, so we'll cancel those ones out. 4, 3, 1, 2 actually showed up in state 3, so we don't need that one. 1, 3, 2, 4 is okay, and then 3, 4, 2, 1 also showed up in state 3. So we only have 3 new additions here. 1, 2, 3. So these are the 3 buttons that could not have been obtained in the previous 4 steps because they are new unique additions to our list. Therefore, the answer here, through a systematic approach with a tree diagram, shows us that there are 3 numbers not on Imani's list. That wraps up this week's problems. Check out the problems I've posted for next week's video. Try them on your own first. See how you would approach them. Next week, we'll see the solutions for these 2 geometry problems. As always, if you found this helpful, don't forget to give this video a like and subscribe so you don't miss the next one.
That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.